Hello and welcome. Today, we will explore the critical considerations for loading data into Snowflake. Whether you are migrating a massive historical dataset or setting up a daily batch process, understanding how to prepare your files, configure your resources, and handle errors is essential for performance and cost efficiency. Let's get started. Your first consideration is selecting the right ingestion method. For large, existing datasets, bulk loading using the copy into command is the standard approach. It relies on user-provided virtual warehouses and allows you to load batches of files from cloud storage. Alternatively, for continuous, small volumes of data, Snowpipe offers a serverless model that loads data within minutes of file arrival. While both methods support basic transformations like casting or reordering columns during the load, we will focus on the considerations for bulk loading today, as it is the foundation for understanding Snowflake's ingestion architecture. This diagram illustrates the decision path for data loading. Starting from your data source, you must decide the load type. If you have large volumes or batch requirements, you utilize bulk loading via the copy into command, which leverages your user-managed virtual warehouse. If you have continuous data streams, you opt for Snowpipe, which uses Snowflake's serverless compute resources. Both paths ultimately land your data into the target table. A critical, often overlooked consideration is file sizing. To optimize performance, you should aim to produce data files that are roughly 100 to 250 megabytes in size. This is because Snowflake processes files in parallel. The number of load operations cannot exceed the number of files. If you attempt to load a single 100 GB file, only one compute thread can process it, leaving the rest of your warehouse idle. By splitting large files into smaller chunks, you allow the load to distribute across the available compute resources, scaling linearly. Visualizing the impact of file sizing. On the top path, a single large file forces a single processing thread, resulting in a slow load. On the bottom path, we split that same data into multiple 100 MB files. This enables parallel processing, where multiple threads represented here by thread 1 through 4 ingest the data simultaneously, resulting in a significantly faster load. How you organize files in your stage affects load management. We recommend partitioning data using logical paths that include details like application, location, or date, for example, organizing by year, month, and day. This granular structure allows you to copy specific subsets of data into Snowflake with a single command. Furthermore, because cloud storage transmits a directory list with each copy statement, reducing the number of files in a specific directory path improves the performance of your command. You can also combine paths with pattern matching to precisely target the files you need. Here we see a structured directory hierarchy. The S3 bucket branches into application folders, then time-based folders for year, month, and day. This structure allows a specific copy into command, shown at the bottom, to target only the 01 directory. This avoids scanning unrelated files in the 02 directory, optimizing the load operation. For compute resources, best practice is to dedicate a separate warehouse for loading operations to prevent impacting your analytics queries. Regarding size, bigger isn't always better. Unless you are loading hundreds of files concurrently, a small or medium warehouse is generally sufficient. Increasing warehouse size only improves performance if you have enough files to utilize the additional threads. However, if your load involves complex transformations or large semi-structured data that requires significant memory, a larger warehouse may be necessary. This flowchart guides your warehouse strategy. Starting with the workload, check the load type. If you have a high file count or complex transformations, you should scale up the warehouse. If you have a low file count, a small warehouse is sufficient. Crucially, the dotted line shows isolation. Your loading warehouse should be separate from your dedicated query warehouse to ensure stable performance for end users. When loading semi-structured data like JSON, Snowflake's variant data type offers great flexibility. However, specific considerations apply. Elements containing null values are not extracted into optimized columns by default. To optimize storage and query performance, we recommend setting the file format option strip null values to true. This removes object elements containing nulls, allowing Snowflake to better optimize the remaining data structure. Also, remember that non-native types like dates are stored as strings within the variant. This flow demonstrates handling JSON nulls. If your JSON file contains nulls and you perform a standard load, top path, the variant column stores explicit null strings, which can hinder optimization. By choosing the bottom path and setting strip null values equals true, Snowflake removes these null elements, resulting in optimized columnar storage for better performance. Finally, consider how you handle errors and cleanup. The on-error copy option lets you decide whether to abort the load, skip a specific file, or continue processing when errors occur. Before running a large load, you can use validation mode to return errors without actually loading data. Once data is successfully loaded, it is best practice to remove the staged files. You can do this automatically during the load by setting purge equals true in your copy command, or manually using the remove command later to maintain hygiene and reduce costs. This process flow details the execution logic. First, you decide if you are in validation mode to simply check for errors. If loading, the on-error setting dictates behavior. Abort stops everything on failure while continue loads valid rows despite errors. Finally, upon load success, the flow moves to purge or remove files, ensuring your stage remains clean.